All right. Let's look at an application of Le Chatelier's principle, which we learned about a couple of sessions ago. Specifically, this process is called the Haber Process. The Le Chatelier's principle is very important in industry because if we're not going to be efficient with what we're doing, money will be lost, and that is what drives the world. So they want chemical engineers want to utilize Le Chatelier's principle to make things as efficiently as possible. Very famous example is making ammonia, yes, NH3. It's used in many things. The biggest one, fertilizer. So this a man named Haber came up with the most efficient way to produce ammonia. So we have an equilibrium here, and I'm interested in what sort of things can I do to this equilibrium to increase the formation of this. That means I want to shift this thing to the right. I want to shift to the right. So I want you to pause for a second, and I want you to all I want you to do is, what are the things? I don't for example, temperature. Temperatures is an answer. What other things, what other stresses might I put on this system to shift the equilibrium? I'll pause. All right, so I can increase, I can change temperature. Another stress would be changing concentrations. Yes, I can put a stress of pressure on this, and there's one other thing that I might do. I might add a catalyst. We'll start with the catalyst first. Yes, if it's already at equilibrium, a catalyst won't do anything. However, if it's not at equilibrium, it will make it get there faster. So yes, I want a catalyst here. I want an iron oxide catalyst. Okay. Will be present in order to make this this energy barrier from here to here and back and forth, make it smaller. Let's talk about concentration. What will concentration do? I want to make more of this, so if I want to shift this thing to the right, what should I constantly be doing with this? I should be suck out NH3. If I suck out NH3, this stuff will make more to replace it. And if I take more out, this will make more to replace it. So I'm constantly driving it this way if I'm constantly sucking out NH3. And on this side, what should I do to the concentrations? I should constantly be adding it in. I'm constantly adding these in and sucking this out. It's constantly going to be driving this way to make more NH3. So there's concentration. Pressure. If I increase the pressure of this whatever vessel we're doing this in, let's say let's start with going with increasing the pressure. If I increase the pressure, yes, doesn't like it. It wants to undo it. Wants to undo this change. So if it wants to undo it, it wants pressure to go back down. So how can I do a pressure change? Over here on this side, I have 2 molecules. And on this side, 1 and 3 makes 4 molecules. So which side shifting to which side will drive the pressure down? It's this way, yes? Shifting to the right, and that's what I want, yes? So it would seem as if I want to do this at a high pressure. Pressure goes up, this system doesn't like it, it will shift to the right so that 4 become 2, 4 become 2, 4 become 2, and eventually I have less molecules in the container and the pressure starts to go back down again. So I want to do it under high pressure. I want to suck out NH3 and I want to add these in. I want to put in an iron oxide catalyst. Now the last one is temperature, and it's a bit more complicated. So let's think about this as heat. Yes? So if I increase heat, add heat in, this, just like concentration, this would go up if temperature goes up. Yes? So if this goes up, this equilibrium does not like that, and it will move to use this up. It will shift left, and that is not what I want. So let's say that I shift the temperature down. If the temperature goes down, does this equilibrium like it? No, it wants the temperature to go back up. How will it get the temperature to go back up? It will shift right. And this is what I want. By shifting right, I would be making more NH3. So we want temp to go, we want temp low. Yes? Now, however, if the temp is low, what happens? The rate is slow. And we don't want that either. We don't want people sitting around. If you own a business, you don't want paying people to stand around waiting for stuff to happen. So this is a conflict between yield, how much NH3 I can make, and rate. So there are two competing factors, and right now they're opposing each other, because to get a really good yield, I want the temperature low. That makes the rate bad, and if I want the rate to be really good, I would put the temperature up, but if the temperature goes up, the yield goes down. So we choose a middle temperature, and it seems like it's not very middle maybe, but 500 degrees Celsius is the maximizes what you want. And they would have done experiments, they would have plotted a graph for fans of calculus, and they would have looked for where I get a peak. They would use some calculus there. These are the factors that affect this reaction: temperature, pressure, concentration, and a catalyst. And now you've seen it in action, how I could use Le Chatelier's principle to maximize the yield of a product.